Thank you. Thanks everyone for coming. So my goal today is to entertain you with some mind-blowing facts about the universe, maybe cause some existential crisis along the way, and also convey the idea that it's a very, very special time for cosmology right now, and I'll show you why. So we live on our planet Earth. Everything that we know has happened here. All of our problems, our mistakes, the taxes that we had to pay, everything happened here. Our precious planet that is at a very precise equilibrium to allow life, and it's the only planet for now that we know of that has life. But beyond the Earth, in space, there is a whole variety of celestial objects. There are other planets, like Jupiter in our solar system, but also exoplanets outside of our solar system that revolve around their star. There are many, many stars like our sun. There are also dead stars that emitted very high energy and a lot of matter, and you can see the remnants of it in planetary nebula, which you might see tonight through the telescope. There is dust, there are black holes, like at the center of our galaxy, the Milky Way. And there are other galaxies that also have many, many stars and many, many exoplanets. And there are many, many of those galaxies. So now you should feel like a speck of dust, and that's normal. So that's to say that the universe is, like everything that's in the universe is very diverse. There is a whole variety of different objects. And the universe contains everything. That's by definition, that's what the universe is. And in cosmology, the question we want to answer is, what can we say about the universe? What is it made of? What is its story? And it seems impossible that we can say anything like that because it's so, like, there is so much different stuff. But what we do in cosmology is that we take a step back, we zoom out. So the sun is in our solar system, which is in a spiral arm of our galaxy, the Milky Way. The Milky Way is in a group of galaxies where the other main galaxy is the Andromeda galaxy, the closest galaxy to us. This group is within a cluster of galaxies, which is in a supercluster, which is in a massive web of matter. So I think now that's maximum existential crisis. We are like absolutely nothing on the size of the universe. And when you zoom out on these distances that are like billions of billions of billions of miles, like you don't even talk about miles, you talk about light years, the time it takes for light to cross, travel for 1 year. And at these scales, the universe looks like very uniform. It looks kind of the same everywhere. And that's one of the bases of cosmology, and that's why we can say something about the universe. So I have to tell you about one of the first questions that we... Is it a problem with my mic? Okay. That's weird, but okay, if that's okay. So one of the first questions that we had more than a century ago was, how big is the universe? Because at the time we thought our galaxy, the Milky Way, was the whole universe. And I have to tell you about this because this involved Curtis from the Lick Observatory, where we are today. So in 1920, people wanted to organize a debate at the Smithsonian in DC. And one of the organizers were hesitating between talking about general relativity, so Einstein's theory of gravity. And one of the organizers was like, I don't want to do that because no one understands general relativity and I never want to see this theory ever again. So instead, why not have a debate about how big is the universe, which I found was a very amazing question to ask because it's so simple but has so much impact and consequences. And this question came out because in the 1920s, they started to observe what they called spiral nebulae like this, which we know now are other galaxies like Andromeda. And the question was, are they inside or outside of our Milky Way? How far are they? So Shapley from the Mount Wilson Observatory, which is just by Los Angeles, near where I live, came and presented the arguments to say that those spiral nebulae are inside of our Milky Way. And actually, his arguments during these great debates were actually apparently pretty simple, and his goal was mainly to shine in front of people from Harvard because they would hire him later on as a director, which I find deeply hilarious and very like how it works in academia, you know. And on the other side, we had Curtis from the Lick Observatory, who presented all of his arguments saying, no, the spiral nebulae are outside of the Milky Way, and the universe is much bigger than we think. And later on, of course, in 1924, Hubble showed that those nebulae are like island universes, as they call as Kent said, they are actually outside the Milky Way, and the universe is much bigger than we think. And this was the start of modern cosmology. So, of course, for millennia and millennia, people in many cultures had their own explanation for the universe, the history of the universe. But here I'm mostly going to talk about modern cosmology, where we have a mathematical description and we verify it with observation. And I'm going to talk about the status of it today and in the future. So modern cosmology is actually a very recent science. It's barely a century old. And how did it start? So Einstein developed his theory of general relativity, where he was basically saying gravity is a property of space-time. It's a geometrical property, and the universe is basically space-time. And then later on came Friedman, Lemaitre, Robertson and Walker, who applied Einstein's equation of general relativity to the universe. And their equation showed that the universe is expanding. This space-time is stretching with time. And this was later on proven observationally by Hubble at the Mount Wilson Observatory, based on the previous work from Henrietta Leavitt and Slipher, and showing that the galaxies are receding from us, and the furthest galaxies are receding faster. And that's exactly what happens in a universe that's expanding. So that was at the end of 1920s. And so that is kind of mind-blowing, and actually Einstein didn't think the universe was expanding. He thought it was a static universe. But clearly, at that time, it was clear the universe is expanding. And that has tremendous consequences. In particular, that means the universe has a beginning. Because if you go back in time, then the universe is smaller and smaller, hotter and hotter, denser and denser. And at some point, you can't explain the universe anymore because we don't have the tools to describe it because it's too hot, too energetic. And that's the Big Bang. So basically, since the Big Bang, the universe has been expanding and has gone through different phases. And for instance, today, galaxies forming and just evolving. And now, after those many, many years of development, we describe our universe very simply by just a few equations. And the main principle is that the universe today is mainly made of dark energy and dark matter. And we call it the lambda CDM model. And the other basis of this model of our new universe is that general relativity is the theory of gravity, the theory that we use to describe gravity. Okay. And since the 1920s, we made many, many cosmological observations, and which maybe pay attention to just those circles here. Those are measurements, and the bars around it are error bars showing our uncertainties on these measurements. And all of these data points, which come from different type of observation, we can predict one curve that goes through all of those observations. That's the lambda CDM model. So I think that's my way to fight the existential crisis, is that the universe is like 15 billion years old, 90 billion light years wide, but we are able to describe it very simply, and we have the tools to explain it. And I think that's very powerful. But I said it's mainly made of dark energy and dark matter. Okay, so actually when we look at the sky, we see the light coming from the stars, from galaxies, and this light is only the visible tip of massive dark matter structures in our universe, okay? And most of the matter in the universe, 85% of matter, is dark matter. Dark matter is something that doesn't emit any light. It doesn't interact through any forces except through gravity because it has a mass. We have no idea what it is. And it's mostly what makes up the universe, so that's a big problem. However, we understand gravity very well. So we can tell our computer how to predict how the matter is distributed in the universe. That's where this came from. So we call this the cosmic web. It's a web of dark matter where you can see so the purple is where matter is, and the brighter it is, the more matter there is. So you see how the cosmic web is structured in filaments and like nodes in between these filaments, and galaxies live in cocoon of dark matter. So I want to note here, because we're going to talk about her again, that Vera Rubin was one of the first person to show that dark matter existed. In the 1970s, she was measuring with her collaborators the speeds of stars rotating around galaxies. And she showed that stars away from the center of galaxies were going faster than expected. That means there is more matter than we see, because they are going faster. Like, for instance, Jupiter, which is further than Earth from the sun, goes slower than the Earth around the sun. And that's not what you see at the scale of a galaxy. So there is something more. So that was a massive step in cosmology to show that there is dark matter in the universe, and it actually makes up most of the matter. So that's another existential crisis, is that the matter that makes us and everything around us is only like 15% of matter. So it's ridiculous. And so at the moment, we have many ways to explain dark matter, but we have no observation that indicates what it is really. So these are like different explanation, like different type of particles. So for instance, it could be a particle that interacts, but very, very weakly, so weakly that we've never seen it interacting through like the fundamental forces. There are different ways to look for dark matter. We can look at it in large particle colliders, like the LHC in Geneva, which is the largest particle accelerator on Earth right now. Or we can put big cylinders of liquid miles underground and wait for dark matter to hit one of the atoms in the liquids to detect it. Or we can wait for dark matter in the universe to interact and then release a lot of energy in gamma rays and detect it. So these type of search are ongoing, and we're making more and more precise more and more powerful experiments to detect it, but for now we have no indication of what dark matter is. But what I'm going to actually mostly focus on is dark energy. So another dark thing, because we also don't understand what it is. So the expansion of the universe has actually been accelerating for the past 5 billion years. Okay, and in a universe with mostly matter, because of gravity, the expansion would slow down. And we observe exactly the contrary. So to explain it, we say that most of the universe today is dark energy. And this was observed the first time in 1998 with supernovae. So supernovae are big stars that are like exploding and releasing a ton of energy. Like you can really see it as bright as a galaxy when it happens. And the brightness of a supernovae is known, so you can tell how far a supernovae is this way. So several teams in 1998 presented their results where they showed that the supernovae that are really, really far are actually receding from us even faster than we expected. There is dark energy, and that was a surprise, and they were awarded the Nobel Prize for this discovery. So what is dark energy? So in our standard model of cosmology, the way we describe the universe, we just say that it's a constant in our equations. We call it the cosmological constant lambda in our equations. And this corresponds to the energy of the vacuum. You have to understand something about dark energy. It's very weird because, you know, like matter, if for instance, let's say you blow in a balloon, the air in the balloon, when it stretches, it's going to just dilute in the balloon. Okay? Dark energy, the density stays the same. So we stretch the balloon, for instance, there will be more dark energy. So we think it's the energy from the vacuum that's just created because there is more space, basically, and that's kind of acts like a repulsive force that caused this acceleration of the expansion. But the problem is that when theoretically you try to compute how big is this energy, you have a complete mismatch between what we observe and what we compute, like 10 to the power of 120. That's the most massive mismatch in science. So there are other questions that we ask, like other alternative. Is it not a constant at all? Does it change with time? So, and that's why at some point it started to make the universe expansion accelerate. Or was Einstein wrong? Was one of the bases of our model, general relativity, is it wrong? That's what I work on. Or is there a fifth fundamental force in addition to gravity, electromagnetism, and the weak and strong force? So understanding what is dark energy is a big goal of cosmology today. So how can we probe and explain what it is? So we can either observe supernovae, like they did when they discovered dark energy. That means measuring distances to see how fast the universe is expanding. But we can also observe this web of matter to see how fast it grows. Indeed, again, you can put in a computer the equation that tells you how matter grows in the universe. And if you start from this, again, those are like large distances, the matter is going to start to structure more and more because of gravity. You see it form more and more filaments and clusters. Okay, so if there is no dark energy, the structure will be even more like collapsed. There will be more bigger nodes of high density of matter than if there is dark energy. Because dark energy is a repulsive force, so matter has to fight against it to collapse because of gravity, basically. So you can see that by mapping the cosmic web, we can tell if there is, we can tell something about dark energy. But again, most of the matter in the universe is dark matter. And dark matter doesn't emit any light. Okay, but dark matter interacts through gravity, and gravity interacts with light. Indeed, so again, think about the universe as space-time, like a sheet of paper, and a mass will deform space-time. Okay, and imagine a star that's emitting light, a photon. So light in the universe, if there is nothing, it just goes straight. But if there is something, a mass that deforms space-time, then the light will be deviated, it will be bent. And so then on Earth, when we look at this light, we'll think that this star, instead of being, for instance, behind the sun, is actually over there. And that's called gravitational lensing. And that's actually how general relativity was verified for the first time by Eddington, by looking at the lensing of stars behind the sun during a solar eclipse. And that he showed that the position of stars was shifted because of this effect. Okay, here I'm showing the effect of like putting a lens in front of a grid that I drew, just to show that it kind of really is just like the mass acts as a lens. And if you take pictures of galaxies, you can get this type of images. Those galaxies here, they are normal galaxies, but it's just that they are behind a big mass. And because they're behind a big mass, their light is deviated, and that's why they get stretched like this. So you can see these very kind of like striking features of gravitational lensing. And so gravitational lensing reveals where is dark matter. So this is a beautiful example from this cluster. I think it's called cluster 0024, whatever. I don't even know where it is. But so that's from Hubble. And you can see here those galaxies that are stretched because of the mass from this group of galaxies. And this is what we predict where the dark matter is because of this lensing effect. So in cosmology, we don't know what dark matter is, but we know where it is, and we understand it very well. And so what I showed here is actually quite extreme case where you have an alignment between the galaxy and a big mass. But actually, all galaxies in the universe are slightly stretched like that because of gravitational lensing by this big cosmic web. But it's a tiny effect, and it's called weak gravitational lensing because it's so tiny. And the thing is that we don't know the original shape of galaxies. But on average, galaxies are like circular. If you, some are like very weird, but like on average, they are kind of circular. And weak gravitational lensing will add a slight ellipticity to the galaxies. So by imaging many, many galaxies, so I'm talking thousands or millions of galaxies, we can reveal the cosmic web through weak lensing, and this way understand dark energy. And again, this measurement of weak lensing, the first one was made in 2000, so that's only like 23 years ago. It's in science, that's a very, very recent thing. So what we do today is try to image many, many galaxies again. So when I started my postdoc in the UK, I joined the Dark Energy Survey, which is using a telescope, the Blanco 4-meter in Chile, and imaged the sky for 6 years, from 2011 to 2019. Okay. And I actually had the great opportunity to go to the telescope to participate to the observations. And that's showing the dome opening and the telescope here with the mirror at the bottom, which we can't see, and the camera up here. So the light, during the night, the light from galaxy goes through the dome, hits the mirror, and goes into the camera. And then the camera sends us information that then we can analyze with our computers. And that's the type of images that we get. Like, we don't really care about one galaxy. We want many, many galaxies so that we can measure their shape and measure weak lensing. And this is me with one of my colleagues, Rachana, just enjoying being at the great telescope. So after many, many years of work, it takes a long time to analyze this data, and actually we are still analyzing them. But recently, we revealed the cosmic web in this patch of the sky here. And for 4 years, with one of my colleagues, I collected an analysis where we use weak gravitational lensing from the Dark Energy Survey to test if the dark energy is really a constant, and to test if Einstein was right or not. So we are an international collaboration spread out all over the world. So most of our work is on Zoom or Slack. We use supercomputers and to make big computation. We code a lot and we read papers and textbook. And after many years of hard work, we finally published this year our results and showed that the cosmological constant is still a viable explanation for dark energy and that Einstein is still right. But for how long? Okay? Because now we are going to start having like the next generation of galaxy surveys. For instance, the Vera Rubin Observatory, so named after Vera Rubin, I talked to you about before. And actually, originally, that was called the Dark Matter Telescope. But actually, now it's called the Rubin Observatory. And it will start surveying the sky in 2025. I, again, had the great opportunity to go to the telescope last March. So right now, it's under construction in Chile, on the mountain just next to the Dark Energy Survey, on Cerro Pachón. So the building is almost finished, and this is the telescope. So I'm not sure you can really understand here, but this is 8 meters wide. It's absolutely ginormous. And it goes super fast, like it moves really, really fast. It's very impressive. So there are no mirrors yet, but actually now I think there are. But here I'm showing you the hole inside the building. So that's inside this building. They are like putting there was a mirror here and here, which they put on the telescope. So I want to show this because this is incredible. This is one mirror, but there are actually 2 mirrors. So this telescope has 3 different mirrors. So the light bounces off the first one, then will bounce off the second one, and then we'll go back in the middle of this same like piece of glass. There is like a third mirror that will then bounce the light up to the camera that will be there. This is incredible, and all of these mirrors weigh a lot, and they had to do a lot of technical developments to make that work. And then they will put in the camera here. Oh, I just wanted to show you this, because actually that's something that was very impressive to me, is that there is a massive chamber, again, in this building, because they will need to put aluminum regularly on the mirror, so that they keep their shine and they keep reflecting the lights. And so they will take the mirror off the telescope, put them in there, and aluminize, like, on the spot. That's incredible. That's a big machine. This is fun. There is one tunnel that you have to go through to get to the telescope, and this is just to show that the mirror were fitting exactly through this tunnel. That's one limitation of the size of the mirror. The camera, it's the largest camera ever built, okay? It's 200 CCDs, 3 billion pixels, so like 100 times more than your iPhone. And this is how it looks like. It's at Slack right now. Actually, I took this picture. And it's really funny because it looks like the lens of a DSLR, but it's just my size. So it's like gigantic. So it's still at Slack right now. They're doing the last test, and it will be shipped to Chile soon. There is a whole thing about it has to go on a plane. Like, you want the plane to be very stable because this is very, very precious camera. But yeah, it's very exciting. People are very stressed out at Slack, but it's coming together. So with the Rubin Observatory, we will image 20 billion galaxies. I mean, this is incredible. It's a huge step for weak gravitational lensing. And in one of my papers, I showed that we could expect to test gravity, Einstein's theory of gravity, with 10 times better precision than today. But the other side of the observatory is that it's really fast, so it's going to visit the same part of the sky multiple times. And it's actually going to image the whole southern hemisphere every 3 nights for 10 years. And so that's a very powerful kind of property, because we'll basically revisit the same part of the sky, and we will be able to see if something appeared or something moved. And you can do the difference between two images and see what's left out. And that's, for instance, very good for supernovae, because basically supernovae, there is just like suddenly a star dies, like explodes. You can't predict it. You have to wait for it to happen. Like here, that's an example here. So we expect millions of supernovae compared to thousands today. So that's, again, a huge step. And it's also very useful for solar system, so we'll be able to map bodies of the solar system, check out if there is any asteroid coming to Earth. So that's also another useful aspect of the Rubin Observatory. And that's not the only telescope that's going to map galaxies. Okay, there is also from Earth the DESI from Kitt Peak Observatory in Arizona, and it's taking data right now. I also want to say that the Euclid satellite from the European Space Agency, but the US is also involved in it, will actually launch next week from Florida from a SpaceX Falcon 9 rocket, and on Sunday, the 1st of July. This is, again, another amazing step. It's going to do something similar to the Rubin Observatory. And later on, NASA will launch the Roman satellite. So we have all of these machines to measure dark energy, okay? But there are also, I'm just going to check the time. Okay, good. There are also other problems that we have in cosmology today that I think we're going to solve very soon, because we are putting everything in place to solve it. What happened just after the Big Bang? So we think, and we need actually cosmic inflation to happen just after the Big Bang. So what is cosmic inflation? It's an exponential expansion of the universe. And we need it because of this massively accelerated expansion just after the Big Bang. There were tiny fluctuations of matter that suddenly grew and became the matter distribution that we see today. So that's another existential crisis, that we all come from quantum fluctuation of matter produced during the inflation. You're welcome. And so after the cosmic inflation ended, so the universe continued expanding, and then it's accelerated again. So we want to see if cosmic inflation really happened. But so we have to look far back in time, so we have to look at light coming from faraway galaxies. But actually, there is a limit to how far back in time we can look. The last thing we can see is the first light ever emitted by the universe, and that's called the cosmic microwave background. So after the Big Bang, the universe basically was a soup of light and matter, and light was opaque. Light couldn't propagate because it was always hitting matter on the way. And at some point, the universe got cold enough, like it was expanded enough, so that the light was free to go. And that's what the cosmic microwave background is. It's this light that is traveling the universe, and we can measure it today. So we can't see behind the cosmic microwave background. So how can we test if cosmic inflation really happened? So you have to bear with me a bit here. So that's matter today. Okay, that's how we think it structures the cosmic web. This is how the matter was distributed like 300,000 years after the Big Bang, as we can see in the cosmic microwave background. So this light, the CMB, the cosmic microwave background, that's like all around us and that we can measure, it actually has tiny fluctuation of intensity, tiny fluctuation of temperature, and that corresponds to how the matter was distributed at that time. And actually measuring those tiny fluctuations, that was also a ginormous step for cosmology that happened in the 90s. In the 90s. And again, people got the Nobel Prize for it. And during cosmic inflation, there are gravitational waves that are produced. There are ripples of space-time. And that will imprint in the cosmic microwave background in the polarization. So not the intensity, but the polarization. That's another property of light. It's the direction of the electromagnetic fields, basically. But it's just to say that there is this one other property of the cosmic microwave background that can show that cosmic inflation that we need to explain our universe happened. And that's the goal of many, many telescopes right now. And we need to put those telescopes high up so that there is less atmosphere, less water vapor on the way. So they are either in Chile or at the South Pole. And in the coming decade, so actually next year, we will see the Simon Observatory. So earlier I was talking with Paul, observatories are called after the people who who do the finance. Actually, it's the Rubin Observatory. It's not. It's for the science, but in this case, it's for the people who fund the observatory. So I thought it was interesting. So that will be a group of telescopes in Chile that will look at try to detect cosmic inflation. But over the next 10 years, the whole community of cosmic microwave background will focus on what they call S4, which is a whole system of like 20 telescopes that will all look at this polarization of the cosmic microwave background. So over the coming decades, we will get terabytes of data from the most precise, the largest telescopes. We are developing new tools. We will be using new tools like artificial intelligence or machine learning. And we all work together in large international collaboration. And all that for dark energy, dark matter, and cosmic inflation. And there are also other questions that I think we will answer with all these developments. How fast is the universe really expanding? Because right now there is kind of like a debate on what the actual value is. And what is the mass of the neutrinos? These are a type of particles, and we actually don't, we know they exist, we understand them quite well, but we actually don't know their mass. And cosmology can help for that. So I think we have to meet again in 10 years, because I think there will be incredible, we will have answered some of these mysteries, I think, for sure, because we put so much money, time, and people in these telescopes. I think we will definitely make big discoveries in dark energy or cosmic inflation. And I also want to say that it's like an extremely exciting field to work on, and a part of my work is also ensuring that anyone who wants to work on this is welcome and feels like included, because it doesn't have to be the same people as 100 years ago who do these discoveries. Everybody is welcome to join, and also as citizens there will be many opportunities to participate. So yeah, I can't wait to see, and I hope as well you too, and we meet again in 10 years. Thank you.
Why is the mass of that neutroni or whatever it was at the very end that you mentioned? Why is that important to know the mass of that thing?
Yes, because so there is also a model of particle physics, and our goal is also to know all the properties of the particles. Like we know everything, even the Higgs boson, we understand everything. But this is still like a missing piece. And actually, in cosmology, we want to know what it is because it has an impact on the way matter is distributed. We always need to measure things more and more precisely. So, and yeah, that's one of the remaining big questions in particle physics as well. Yeah, I guess. Yeah.
One of your early slides, you showed the size of the universe. It's 93 billion light
Yes.
I've never heard that that estimate. Is there a layman's way to explain how you can figure that?
Yes, so actually what I mean by it is what we call the observable universe. It's a light coming from the furthest galaxy possible. So the distance that the light took from like the furthest galaxies that we can see. That's what I mean by this size. Because we actually think the universe is infinite. But we only have access to a part of this universe because of the finite speed of light. So we can only see light from this far away. But this is a diameter, so maybe you might have heard like 40 billion years. This is for the radius of the observable universe. If that makes sense.
Okay, find more.
Oh, no.
Go ahead.
Yeah.
I just had a question in terms of determining things like the expansion rate of the universe. When you take a picture of the night sky, you have information there that is billions of, that information, those pixels are billions of years, that the source of that information is billions of years of difference. It'd be like taking a picture of this room
Yes.
every day for a year, let's say, and then superimposing all the pictures and making determinations about me relative to somebody else in the picture who we didn't even maybe coexist at the same time in the room. How is that reconciled when you try to do these computational distance measurements?
Yes, so it always, I always have trouble thinking about that. Indeed, measuring distances in an expanding universe is very complicated. That's why we have to use supernovae, etc. But we take that into account. If you want, like it's the integrated distance between when galaxies emitted the light until today, and we take that into account in our computation. And that's how, for instance, we know there is dark energy because on the way light had time to feel the expansion. So yeah, we describe it in this way. Yeah.
Okay,
Yeah, great question.
Draw a close to this session. It was your tax dollars at work a little bit with all these new facilities coming online, only to be told that we have to meet again in 10 years. I think we have to book the band to do a long So in the meantime, we'll thank Agnes again.
Thank you.